Welcome students. Today we are going to study about the concept called to be equipotential surfaces. What do you mean by the concept known as equipotential surface? The name itself is self-explanatory. Equipotential surface, or we can say it out as equipotential surfaces. What do you mean by this? Equipotential surface or equipotential surfaces. You see, the name itself is self-explanatory. A potential which is considered to be equal or same at all points in an electrical field or at different points in an electrical field. So that surface we are calling it out as equipotential surface. How we can explain or how we can define? So I can define like this. Equipotential surface is a one or is a surface on which the potentials are taken to be, the potentials are same, not taken to be same, potentials are same at different points, that we are calling it out as equipotential surface. See, we are going to study the equipotential surface in two cases. One, for a point charge. So, for a point charge, how will be the equipotential surfaces? Similarly, the second one, for an uniform electrical field. For an uniform electrical field, how will be this equipotential surfaces? These two we are going to study today, and also the properties of equipotential surfaces. First of all, let us consider a point charge. So, if you are taking a point charge, I am considering the point charge as a plus Q. If you are taking a point charge, around this point charge you will be having the electrical field. Always the electrical field is represented by drawing electrical lines of force. When you are considering a point charge, electrical lines of forces are acting radially outwards. In this electrical field, you consider any point from the charge. If you are considering the point is at a distance r1 from this charge, then the potential, let us consider it as V1. We know that the potential at a point due to a point charge is 1 by 4 pi epsilon 0 into Q divided by R. If it is R1, it is R1. So you consider another point here, another point here, another point here, another point like this. You consider different points, but all the points are at the same distance R1. The second point is also at a distance R1, or the final point is also at a distance R1, or if you are considering this point, this is also at R1. If the distances are R1, then we know V1 is inversely proportional to that of R1. So at a distance R1, at all these points, we are having the same potential V1. If all these points are joined, you can able to get encircled. So, if you are taking another point at a distance R2 from the center, and if you are joining all the points which are at a distance R2, you can get another circle. So, we can state that for a point charge, okay? So, we can state that for a point charge, equipotential surfaces are in the form of concentric circles, From the diagram itself we can say the equipotential surfaces are, okay, equipotential surfaces are perpendicular to electrical field lines. So we can say in case of or for a point charge, equipotential surfaces are in the form of concentric circles, and also we can say equipotential surfaces are perpendicular to that of electrical lines or electrical field lines. This is the first case. Let us consider the second case. What is the case number 2? See, we have to calculate the equipotential surfaces for an uniform electric field. In case of an uniform electrical field, how will be the electrical lines or how will be the equipotential surfaces? In case of an uniform electrical field, equipotential surfaces are, okay, we can say the equipotential surfaces are parallel to each other. They are parallel to each other and perpendicular to electrical field lines. Perpendicular to electrical field lines. So, for an uniform electrical field, equipotential surfaces are parallel to each other and perpendicular to electrical lines of force. How you can able to explain this? See, when you are considering a uniform electrical field is represented by drawing parallel lines. If you are drawing parallel lines, then these parallel lines are representing what? These parallel lines are representing an uniform electrical field E. In this uniform electrical field E, if you are considering equipotential surfaces are perpendicular to this electrical field lines, and at different points the surfaces are considered, the surfaces are parallel to each other. That is what I have written it here. Equipotential surfaces are parallel to each other and the equipotential surfaces are perpendicular to the electrical field lines. So this is how we can able to get the equipotential surfaces in case of the point charge and in case of uniform electrical field. Now for this we have to state some properties. Properties of electric equipotential surfaces. Let us consider the first property. What is the first property? We can write the first property like this: work done in moving. Work done in moving a charge. Work done in moving a charge from one point to another on an equipotential surface. On an equipotential surface is equal to 0. What it is meaning? Work done in moving a charge is equal to 0. That is what the concept. How you can explain this? Work done in moving a charge from one point to another point on an equipotential surface is 0. How you can able to explain this? See again, I am considering this positive point charge plus Q. Around this point charge, the equipotential surfaces are in the form of what? The equipotential surfaces are in the form of concentric circles. Okay. Now you consider any one of the circle where the potentials are same. At that I am considering 2 points. One of the point I am representing it as A and another point I am representing it as B. At point A I am writing the potential as VA. At point B I am writing the potential as VB. Now you consider another charge. You take a charge Q to move from the point A to the point B. So in order to move, what is the work done? We have already studied that the work done in moving an unit charge from one point to B to another point A, or I can take as per my diagram work done in moving unit charge. So I am dividing it with the given charge from the point A to the point B is equal to, what is this? We can say that, or we know that the work done in moving a unit charge is equal to the potential difference. So here the work done in moving a unit charge from the point A or to point B or from point B to point A is the difference in potential. So VA minus VB. Since the 2 points on the equipotential surface, we can say the work done is equal to 0. This is the first property. What is the second property? See, the property number 2 is what we have already studied. The equipotential surfaces are, okay, the equipotential surfaces are always perpendicular to electrical field lines. So, equipotential surfaces are perpendicular to electrical field lines. We have to justify this point. How we can able to justify this? If it is not perpendicular, what will happen? Let us consider it in another way or in a contradictory way. If it is not perpendicular means if the electrical lines of forces are not perpendicular to equipotential surfaces, then what will happen? If it is not perpendicular, then we have to consider the parallel component. Then there is a component of the field. There is a component of the field which will be parallel to what? Parallel to the surface. If it is parallel to the surface, that is the electrical component, a component of the electrical field is parallel to the surface, then work done is not equal to 0. Work done is not equal to 0. If work done is not equal to 0 means, but according to the previous case, work done is equal to 0. But the previous case we have proved that the work done is equal to 0. So we can say both are contradictory. Since both are contradictory, it was being proved that, or we can say that electrical field lines are perpendicular to equipotential surfaces. Therefore, we can say that the electric field lines are perpendicular to equipotential surfaces. Okay, let us summarize. See, you just take your notebook and you see what you have written it there. I will summarize what I have told you. What do you mean by this equipotential surface? Equipotential surfaces are the surface on which the potentials are considered to be same at different points. That we are calling it as equipotential surface. 1. The second thing, we have to study the equipotential surface for 2 cases. One is for a point charge, another one is in an uniform electric field. For a point charge, electrical or equipotential surfaces are in the form of concentric circles around the charge in the electrical field. That equipotential surfaces in the form of concentric circles and electrical lines of forces are perpendicular to each other. The second one, in case of an uniform electric field, which is represented by drawing parallel lines, the equipotential surfaces are parallel planes which are perpendicular to the electrical lines of force. So equipotential surfaces are parallel to each other and perpendicular to electrical field lines. Then we have to go with the properties of equipotential surfaces. There are 2 properties. One of the properties is work done on an equipotential surface is equal to 0. Consider 2 points A and B on any equipotential surface, and you have to calculate the work done in moving a charge from one point to another point. The work done in moving a unit positive charge from one point to another point is the potential difference. So work done divided by the charge is giving you work done per unit charge is equal to potential difference means potential at point A minus potential at point B. You just find the difference. Then if you are moving the charge from A to B, then it is VA minus VB equal to 0. Or if you are moving it from B to A, then VB minus VA is also equal to 0, since potential at point A VA and potential at point B VB are equal or same. Then the second one, we are going to justify what we have already studied, that is the equipotential surfaces are perpendicular to that of electrical field lines. How you can able to justify this? If you are considering that the electrical field lines are not perpendicular, then we have to say there is a component of the field which is parallel to that of the surface. If a component is parallel to that of the surface, then the work done is not equal to 0. But in the previous point, we have proved that work done is equal to 0. So both are contradictory. It was being proved on an equipotential surface work done is equal to 0. So it was being proved, or we can justify that the electrical field lines are perpendicular to equipotential surfaces. This is what